Okay, so now we'll shift topics to relations. So first, recall that a relation between two sets, which we'll call X and Y, is a subset R of the Cartesian product of X and Y. So now we'll define a relation on a set. A relation on a given set X is a subset R of the Cartesian product of the set with itself. That is, we're considering ordered pairs of elements in a given set. Now there are several properties that a relation on a set may satisfy. A relation R on a set X is reflexive if and only if, for every element in the set, the ordered pair containing identical elements is in the relation R. That is, the element X is related to itself. A relation R on a set X is irreflexive if and only if, for every element in the set, the ordered pair XX is not in the relation R. That is, the element X is not related to itself. New definition: a relation R on a set X is symmetric if and only if, for every pair of elements X and Y, if the ordered pair XY is in the relation, then the ordered pair YX is also in the relation. That is, if X is related to Y, then Y is related to X. So, new definition: a relation R on a set X is anti-symmetric if and only if, for every pair of elements X and Y in the set, if it is true that both the ordered pair XY is in the relation and the ordered pair YX is in the relation, then X is equal to Y. That is, if it is true that X is related to Y and Y is related to X, then X and Y are the same element. So notice that the terms symmetric and anti-symmetric are not true opposites, and we'll look at an example to clarify this. So let the relation R be the set of ordered pairs x, x, where x is in the set X. Then this relation R is reflexive. Notice that it is also symmetric, and it is also anti-symmetric. So we next will look at a property that is the opposite of symmetry. A relation R on a set X is asymmetric if and only if, for every pair of elements x and y, if the ordered pair xy is in the relation, then the ordered pair yx is not in the relation. That is, if x is related to y, then y is not related to x. So notice that if a relation R is asymmetric, then it is also irreflexive. Oops. Okay, new definition. A relation R on a set X is transitive if and only if, for every three elements, x, y, and z, if it is true that the ordered pair xy is in the relation and the ordered pair yz is in the relation, then the ordered pair xz is in the relation. That is, if x is related to y and y is in turn related to z, then x is related to z. Okay, new definition. Let R be a relation on a set X, and let X and Y be two elements in the set X. If either the ordered pair XY is in the relation or the ordered pair YX is in the relation, then the elements X and Y are said to be comparable. That is, if the elements x and y, either x is related to y or y is related to x, then those elements are comparable. If neither the ordered pair xy is in the relation, nor the ordered pair yx is in the relation, then the elements x and y are said to be incomparable. So two elements in the set X are incomparable if neither X is related to Y nor Y is related to X. So new definition. A relation R on a set X is a total ordering on the set X, if and only if, for every distinct pair of elements in the set, the elements X and Y are comparable, so notice that we are requiring only that distinct elements be comparable, but that all distinct elements be comparable, and if this is true, then the relation R is a total ordering on the set X. If at least one pair of distinct elements in the set X are comparable, then the relation R is called a partial ordering on the set X. So notice that every total ordering is a partial ordering, but not every partial ordering is a total ordering. Further, a total ordering can be irreflexive since we require only that all distinct elements be comparable. Okay, new definition. Let R be a partial ordering on a set X such that the relation R is reflexive, anti-symmetric, and transitive, then the set X together with this relation, which we denote this way, using parentheses, the set X together with the relation R, is called a partially ordered set. Or more commonly, a poset. Now, if, in addition, the relation R is a total ordering on the set X, then the poset consisting of the set X together with the relation R is called a totally ordered set. And there are two other terms to be familiar with for a totally ordered set. A totally ordered set is sometimes called a linearly ordered set, or also sometimes called a chain. So as an example, we will show that the set of integers together with the relation less than or equal to is a totally ordered set. So proof: for every pair of integers a and b, either a is less than or equal to the integer b, or b is less than or equal to the integer a. Notice that this does include the case that a is equal to b, but again, for any pair of integers, one of the following is true: either a is less than or equal to b, or b is less than or equal to a, and so the relation less than or equal to is a total ordering on the set of integers. Now for every integer a, it is true that a is less than or equal to a, since in fact a is equal to itself. And so the relation less than or equal to is reflexive. So now let a and b be two integers, and suppose that both a is less than or equal to b and b is less than or equal to a. Then a is less than or equal to b, which in turn is less than or equal to a. And as a is equal to itself, we have that a must be equal to b. And so the relation less than or equal to is antisymmetric. So now let a, b, and c be three integers, and suppose that a is less than or equal to b, and in turn b is less than or equal to c. Then a is less than or equal to b, which again in turn is less than or equal to c. And so we can read that a is indeed less than or equal to c, and hence the relation less than or equal to is transitive. And therefore, the set of integers together with the relation less than or equal to, where the relation less than or equal to is a total ordering on the set of integers, which is reflexive, antisymmetric, and transitive, and therefore the collection of the integers together with this relation is a totally ordered set.